Okay, so today we're going to talk about infinite sets. Remember last time we defined what finite means and we proved various theorems regarding finite sets, such as the pigeonhole principle or that union of two finite sets is finite. Today we're going to be dealing with infinite sets. Remember, a set X is infinite if X is not finite, meaning that X is not equinumerous with a natural number. Okay. Now, this is the definition of infinity. Like, this makes sense. A set is infinite if it's not finite. There is no natural number and with which your set is equinumerous with. You can try to come up with other equivalent definitions. And one of the most famous ones is, there are many equivalent definitions of being infinite. One of the most famous ones is, I assume, due to Dedekind, because it's called Dedekind, like the notion is called being Dedekind infinite. It's the following. A set is called Dedekind infinite if there is an injection from this set to itself which is not a surjection. In other words, X is equinumerous with a proper subset of itself, okay? Subset of itself. Now, if there's an injection from a set to itself, which is not a surjection, what does this mean? So, X is mapped to itself by some injection. So, for every element in here, you have some element, and distinct elements are going to distinct elements. And this is a map which is not a surjection. Okay? So, there is some element outside the range of F. If you have such a set, you call it Dedekind infinite. Now, why do we say Dedekind infinite? Is it obvious that these sets are such sets have to be infinite? Well, the answer is yes. So this is a stronger notion, being Dedekind infinite. And the proof is as follows. We want to show that every Dedekind infinite set is actually infinite. Assume that, let's prove the contrapositive. X is finite. Okay? Assume that X is finite. Because by definition, being not infinite is the same as being finite. Then, again by definition, there is some natural number n and a bijection f from x to n. Okay? If your set is finite, then it's equinumerous with some natural number. If X were Dedekind infinite, let's pretend that X is Dedekind infinite. Then, by definition, there would be an injection from X to itself, which is not a surjection. which is not a surjection. However, in this case, if you look at the following function, F inverse composed with G composed with F. This is a function from little n to little n. Because you pull it back to x, you apply some function on x, then you apply f back. This is a function from n to n. And this would be an injection which is not surjective. Why? Well, obviously this is a function. Okay, this is an injection. This is an injection. Composition of injections is an injection. However, because G is not a surjection, there is some element outside the range of G. Okay, pretend that that element is x0. So pretend that x0 is not in the range of G. Well, we assume that x0 and n are in a bijection with some f. So, when you look at this function, what do you see? In order for this composition to be surjective, there should be some element at the end which maps to this guy, which maps to f of x0. Okay? But nothing like f of x0 is an element here, but it can't be mapped onto, because in order for something to be mapped onto f of x0, there should be some element who f of x0 should be in the range of this guy, but it can't happen because I assume that, sorry, x0 should be in the range of this guy in order for f of x0 to be in the range of this guy. But x0 is not in the range of this because I assume that x0 is not in the range of G. So this is an injection which is not a surjection. And this contradicts the pigeonhole principle. Okay? So being Dedekind infinite is stronger than being infinite. Now, it turns out that these are equivalent, actually. Okay? We also have an arrow in the other direction. So why haven't I tried to prove that Asst is Dedekind infinite if and only if it's infinite? Because I want to actually make sure that you understand an issue with the proof. It's not an actual issue. You see, in this proof, if you just try to list the axioms we used, you'll see that we never used the axiom of choice. Okay? In order to carry out this proof, you don't need axiom of choice. However, as we shall see, in order to prove the other direction, you need the axiom of choice. And when I say you need, I don't really just mean that we weren't able to come up with some other proof. I mean, it is a theorem that this direction cannot be proven without the axiom of choice. If you reject the axiom of choice, there are set theories where you have Dedekind finite infinite sets. Okay? Now, we want to prove the other direction. For the other direction, we shall need a lemma. And it is the following. If you have an infinite set, then natural numbers inject into that. Now, why is this the case? Let's understand this on picture. Pretend that x is infinite. If it's infinite, it's non-empty. Okay? So there is some element. And I'm going to map 0 to this guy. Now, let's look at the remaining thing. If the remaining thing were finite, if the remaining thing were empty, because this is finite, X would be a finite set. So the remaining thing should be non-empty. So I can choose an element in the remaining thing, and I'm going to map 1 to this guy. Okay, and by recursion, I'm going to continue like that. Now I'm going to remove these two. The remaining thing should be non-empty, because if it is empty, then X would be finite. So I'm just going to choose elements 1 by 1. And that this set is infinite is used in the recursive step. Like, I'm going to say that I can choose a different element than the previous ones because this is infinite. Okay? So this is basically the idea. I'm just going to choose elements of X 1 by 1, and I'm going to say at no stage can I stop because X is infinite. Okay? Now let's write this properly. So let G be a function such that it's defined from power set of X to X, and what it does is for every non-empty subset of X, it chooses one element from that set, and the empty set is mapped to some fixed element. Okay? X is infinite. In particular, it's non-empty, so I can fix some element, and I'm going to find such a function. For each non-empty subset, it chooses one element from that set, and for the empty set, it just sends empty set to x0. Now, why can you find such a function? We need the axiom of choice to have such G, okay? What this function does is, forget the empty set, ignore the empty set in the domain of this. What you're doing is, you have a collection of sets which are non-empty, and you're choosing one element from each of these guys. There was a lemma we proved right after the axiom of choice, which said that we can do this. So in order to construct such a function G, you need the axiom of choice. You first look at the collection power set of X minus the singleton empty set. You say that this is a collection of non-empty sets, so by axiom of choice there exists a function which chooses one element from each of these guys. And then you extend that function to all of the power set. You say that, okay, I'm going to map empty set to x0. This will have no effect on the rest of the proof, but I'm just writing it so that this function is defined on the full power set of X. Now, the reason I chose such an F is such a G is the following. You see, in this, when I told you about the proof, like on this picture, I said that we're going to choose one element from the remaining thing. I should be able to how do I choose one element? I need a procedure which allows me to do that. Well, that's that procedure. This is the choice function I'm looking for, okay? Of course, for empty set, it doesn't really choose an element from the empty set, but I'm just like mapping empty set to some arbitrary guy. Anyway, by recursion, construct f as follows. Now, I want to define a function from natural numbers to x. I can do this by recursion because we proved the recursion theorem, right? Recursive definitions are now justified. I mean, if you want, I can prove using recursion theorem that there exists a function that does what I'm about to describe, but I don't want to do that. Anyway, the function works like this. It maps 0 to x0. And it maps successor of some number to the following element. Let's pretend that I did this construction up to stage n. What do I want to do? I want to choose one element from the remaining set. What's the remaining set? It is the subset of x. Well, it is x minus the stuff I have chosen so far. So I want to get rid of the stuff I have chosen so far. I want to look at the remaining of x, and I want to choose one element from this remaining thing. Okay? So, we can construct such a function. Now, there are two cases. Well, there exists such a function by recursion theorem. There are two cases. At some point, this may become empty, in which case I'm going to choose x0 after that case over and over again. However, an easy induction argument shows that this is never empty. So this needs to be proven by induction, but I don't want to do that. It's an easy argument. This is not empty for all n, okay? And over here, you use the fact that x is infinite, okay? Because if this were empty, then x would be finite. It follows that, now, if this is not empty, then what G does is it chooses one element from this set, meaning that f of n plus 1, f of Sn, is different than all the previous guys. This is different than f of k for all k between 0 and n. And so, f is injective. Okay? Is this understood? This is never empty. So what G G chooses one element from that non-empty set. So f of Sn is necessarily different than f1, f2, up to fn. And this implies that f has to be injective. Okay? Now, questions about this proof? Let's put this little squared. So if you have an infinite set, their natural numbers inject to that set. An immediate consequence of this lemma is that infinite sets are actually Dedekind infinite. Theorem: if x is infinite, then x is Dedekind infinite. Proof: let's say that x is infinite. Let's pick an infinite set. Then by lemma over there exists an injection from natural numbers to x. Now define g from x to x as follows. let's see. This is my infinite set X. By the lemma, natural numbers inject to X. Okay? And I want to define an injection which is not a surjection. What I do is the following. I take an element of X. There are two cases. This element may or may not be in the range of this injection F, okay? So there might be other elements around over here. These guys that are not in the range of F are mapped to themselves, okay? So my G behaves like the identity function outside the range of F. On the range of F, what it does is the following. If X is in the range of F, then X should be f of k for some k, okay? If you have some element on the range of, in the range of F, then there is some natural number mapping to that by definition. What I'm going to do is I'm going to send this guy to f of k plus 1. Okay? So what I'm doing is I'm mapping this x0 to x1. I'm mapping x1 to x2. Okay? x2 is mapped to x3 and so on. Now, as you can see from the picture, the range of this guy will not contain x0. Clearly, x0 is not in the range of this guy. And, okay, I'm going to say clearly G is an injection. You need to check that. You need to check that this is an injective map. Why? Because on this part of its domain, it's injective. On this part of this domain, it's still injective, and these parts do not intersect. You're taking the disjoint union of two injective functions. It's injective. Okay? Sorry, you're taking the union of two injective functions whose domain do not intersect. The union is still injective. Okay? So I found an injective function which is not surjective. So X is Dedekind infinite. You see, in this proof, we actually used the axiom of choice, where in the lemma, to choose those elements, okay, to construct that G. As I said, it is consistent, like drop axiom of choice, just keep the remaining thing, try to prove that infinite implies Dedekind infinite. You cannot. It is consistent with the rest of the axioms that there is an infinite set which is Dedekind finite. Okay? And Dedekind finite means that it's not Dedekind infinite. So, that's that. Questions about this? Now that we have proven infinite equals Dedekind infinite, from now on when I talk about infinite sets, I might use either definition. I might use the definition of being Dedekind infinite, okay? And still say that it's infinite, thus there exists an injection which is a surjection, blah, blah. A set having an injection from to itself, which is not a surjection, is the same as that set being infinite, okay? That's the point. And some of you might have seen this as the definition of infinite set probably in your first year courses, but that's actually the notion of being Dedekind infinite. There are other notions of infinite. I think there's also Tarski infinite sets. I might be making this up, but I vaguely remember seeing something like that. Okay? Most of these notions turn out to be equivalent if you assume all the axioms, but if you drop certain axioms, some of them are not equivalent, like these two. Anyway, questions? Now let's talk about countable infinite sets. Let me erase this word. Definition. A set X is called countably infinite if X is equinumerous with natural numbers. Remember, what this means is there's a bijection from X to N or N to X. There's a bijection between these two sets. Now, you call such sets countably infinite. Why? Because why do we use natural numbers for? To count things, right? We have 0 chalks, 1 chalk, 2 chalks, and so on. We use natural numbers to count things. If you can find a bijection from that, between natural numbers and your set, then you can use natural numbers as labels for elements of X, which means that you can actually count these guys. So this is why it's called countably infinite. Let's make a complementary definition. A set X is called uncountably infinite, or uncountable in short, if it is not countably infinite. Okay. 2 more definitions. I'm just introducing some terminology. A set is called countable, at most countable, or simply countable if it is finite or countably infinite. Now, let's go back to this board. At this point, you should ask the following question. Okay, natural numbers is countably infinite, so it's at most countable. But for the second notion, uncountably infinite, are there such sets? The answer turns out to be yes, as we shall prove next hour. But before that, let's focus on countably infinite sets, like what kind of properties countably infinite sets satisfy. First of all, what are examples of countably infinite sets? The set of natural numbers is countably infinite, almost by definition. The integers is actually countably infinite. We haven't constructed the integers, but I'm going to tell you the bijection between, well, never mind. I will construct those bijections later. So the set of integers is countably infinite. The set of rational numbers is countably infinite. And I'm going to tell you the explicit bijections between natural numbers and integers and natural numbers and rational numbers, but we haven't constructed integers or rational numbers at this point. Those constructions will come next week. When I construct those, I will actually prove that like these are countable because here's the bijection. Okay? But you should know right now that those are countably infinite. What kind of other sets are countably infinite? As we shall see in a second, the Cartesian product of 2 countable sets is infinite. We're going to prove that. And one of our other objectives is to prove that if you have countably many sets, all of which are countable, then their union is countable. So countable union of countable sets is countable. Okay? So, and using just those 2 facts, you can construct a lot of countable sets. So, let's start by a simple lemma. as I said, our target is those two theorems, that countable union of countable sets is countable and Cartesian product of countable sets is countable. Now, the first lemma we want to show is the following. If X is at most countable, then there is a surjection from natural numbers to X. And proof of this, I'm just going to leave that to you because it's easy. It's exercise. By the way, when I assign exercises, you should actually double check. There was one exercise I assigned about ordered sets a couple weeks ago. Like, I wrote one version, then I said that this is also true, and I wrote a second version. The second version was true, the first version was not. And if you're watching the videos on YouTube, you'll see that in the comment section, I actually wrote that like this exercise is faulty. You should have told me this because you're supposed to solve the exercise, but apparently no one worked on that at this moment. Anyway, so work on this. This is true, okay? I promise this is not one of those faulty ones. And I only found one faulty one. Anyway, if X is at most countable, there's a surjection from natural numbers to X. Why? At most countable means that it's either finite or countably infinite. If it's countably infinite, there's already a bijection, so this is trivial. If X is finite, then X is bijected with a natural number. So it's bijected with some n. What you're going to do is, you're going to send, okay, so you're going to send all elements of little n to the corresponding guys. You're going to send rest of the natural numbers to some fixed element, and that would be a surjection. Now, in our lemma, if there is a surjection from some set A to B, then there is an injection in the other direction. Okay? Why? A surjects onto B, okay? All elements of B are covered by these guys. This map need not be one-to-one. I claim that you can find a one-to-one function and injection in the other direction. How? Where would you send this guy? You would send this guy back to this. And you would send this guy back to this. However, if two distinct guys are mapped to a fixed element, you have a problem. Which one are you going to send? Which one of these are you going to send this one to? We have to make a choice, but that's no problem. We can use the axiom of choice to choose one of these guys. And that's exactly what we're going to do. For each little b in B, choose some A sub B, which is in the inverse image of this set. Okay, F is surjective, which means that for each B, if I look at the inverse image of this, this is non-empty. Now, I have a collection of non-empty sets, and I can choose one element from each of these guys. How? We have some choice function using the axiom of choice. Okay, I don't want to write this in full detail, but the actual proof would look like this. By the axiom of choice, you would construct a function from this set to this set, which chooses one element from each of these guys. So f of s is an element of s. And then you would apply this f, I shouldn't call this f. By axiom of choice, you would find such a function h. Then you would apply this h to this guy, and it would choose your A sub B, okay? So this is easy to do, just like that. Just choose one element from each of these guys. Then the map f of b goes to a sub b for all b and b is an injection. Okay? Why is this an injection? Because if a sub b were a sub c, why are you not stopping me? This is not f, this is g. The injection I'm trying to construct is called g. Sorry. Anyway, if a sub b were a sub c, then f of a sub b would be the same as f of a sub c, but f is an injection. That would imply that sorry. This is this phone making me confused. Never mind. Sorry. What was I saying? Okay, yeah, this is an injection. Why? Pretend that this is not an injection. Okay. So B, C, A sub B, A sub C. If these two were the same, because f is a function, I'm just going to use the fact that f is a function, it's not an injection, it's simply a surjection. Because it's a function, B would be C, okay? And in pictorial, this is clear. And it follows from the fact that f is a function implies that it's an injection. Anyway, questions? No? Again, you might have realized that in this proof we used the axiom of choice. Okay, yeah, I really should stop this phone from ringing. Sorry for that. We used axiom of choice for this proof, and again, it's necessary. I'm not going to talk about why it is necessary, because that actually requires some advanced set theory, but you should know that it is necessary. And we proved this lemma, Let's see what we have next. I think we need to prove that subset of a countable set is countable, but before that, let's show that Cartesian product of two countable sets is countable. This Cartesian product is countable. Now, I'm going to leave this proof as an exercise because it will easily follow from the lemma I'm going to write down. Pretend that A and B are both natural numbers. Pretend that you knew that n cross n is countable. Can you use that to show that this is countable? Let's see. This is countable, meaning that n surjects onto this. This is countable, meaning that n surjects onto that. Now, using the surjections, you can show that n cross n surjects onto A cross B. If n cross n is countable, then a countable set surjects onto this. Okay, I'm going to need another lemma for this one. Yeah, I think I mixed up the order of things. Oh, no. I want the following. I want these to be countably infinite. Never mind. This is countably infinite. This is easier. The other one is also true, but we're going to do that later. Anyway, pretend that these are countably infinite. Then there's a bijection between these two. Then there's a bijection between these two. Then you can easily construct a bijection between this and n cross n. Okay? So if you knew that n cross n is countably infinite, then this would be really easy, which is why I assigned this as an exercise. What I'm going to show is that n cross n is countably infinite. Now, there are many proofs of this. I'm going to give you two of these proofs. Well, how do you prove that a set is countably infinite? There are many ways to show it again, but the most direct way is to find a bijection between n cross n and n. Check that this and this are bijections. Okay, I'm going to write down two bijections. I'm leaving it is an exercise to you to check that these are actually bijections. The first one is the following. F of mn is defined to be 2 to the power m, 2m plus 1 minus 1. This is a bijection. And here is the reason. Every positive natural number can be uniquely expressed as a power of 2 and an odd number. Okay? So every positive integer can be uniquely expressed as a product of a power of 2 and an odd number. So if I just subtract 1 from these guys, this will give me a surjection. Okay? Okay, let me rephrase. That every number can be expressed as a power of 2 and an odd number, every positive number can be expressed as a power of 2 and an odd number, shows that this is a surjection because I'm subtracting 1, I'm shifting everything mapped to 0. That the composition is done uniquely would imply that this is an injection, okay? So work on this. It's easy to show that this is a bijective map. The other one I want to give you is called the Cantor pairing function. And as you can guess, it's found by Cantor. Okay, now I have to remember what this was. I think it was this. Let me double check that. Yeah, I should have double checked this before coming to class, but that's okay. Okay, so where is it? No. Yeah, I think this is it. Anyway. Let me show you how this one works, okay? Think of this grid as n cross n. N cross n. Now what this function does is for 0, 0, this is mapped to 0, okay? For 0, 1, what do you get for 0, 1? Let's say that this is m and this is n. For 0, 1, what do you get? 2. For 1, 0, what do you get? 1. Now, for 2, 0, you get 2, 0. 3. 2, 0. 2, 0, you're going to get 3. And for 1, 1, you're going to get what? 2, 3, 4. And you can guess what's going to happen. So you create some kind of snake, which goes like this. It's not really a snake, it just goes like this, okay? This is going to be 15, 16, 17, 18, 19, 20, and so on. It's going to go like this. This is going to give you a bijection between n cross n and n. Of course, this is not a proof that this is a bijection. I was just double checking that I wrote the correct formula, because I always mess this up, the places of mn or maybe plus 1 minus 1. I always mix that up. Apparently, this is the correct one. Now, that this is a bijection requires more work than this, but you can actually check that this is a bijection. Even with more work, you can try to find the inverse of this. But that's more complicated. So this is called the Cantor pairing function. So check that these are bijections. So n cross n is countable infinite. An easy corollary of this is, as I said, if you have two countable infinite sets, you can just prove that their Cartesian product is countable infinite. Now, we're going to show that a subset of a countable set is countable. And then after that, we're going to prove that countable union of countable sets is countable. All those will happen in 10 minutes. Okay, let's have a 10-minute break.